Sum of the forces in? Y, how come? Okay, so we have 500, this is going to be 60 here, right? 500 times the cosine of 60 plus normal B minus weight of A minus weight of B equals 0, right? And normal of B turns out to be 5750. 5750 newtons. What equation you want to do next? Friction equation. Friction of B is equal to mu, which is B, times normal B. So it's 0.2 times NB. So the frictional force turns out to be 1150. And now what do you want to do last? Sum of forces in the x. P minus 500 cosine 30 minus frictional force of B is equal to 0, and P turns out to be 1583. Okay, so what did the question say? It said, find out if the system would be in equilibrium for P is equal to 2500. Well, let's go back to David, your question. Your question was, do we have to analyze the surface of A and B, right? The surface in between. So let's just take a look at this. If we looked at body A, what equation would you do first? Sum of the forces in the y, it would be NAB minus W plus 500 cosine 60. And you would get a value for NAB. And that value, I'm pretty sure I calculated it. Yeah, I got 1750. Did everybody see that? I did sum of the forces in the y equals 0 from this free body diagram. Then what would you do next, David? Okay, let's do sum of the forces in the x equals 0. And we wind up getting the frictional force between A and B turns out to be 433. And can we check this? What? The frictional force from A to B is equal to mu times NAB, right? And what's mu between A and B? 0.3 times 750. What's that turn out to be in math? 0.3 times 1750.
525.
500 what?
25.
Okay, newtons. What does that mean? How come I'm getting two different values?
There's a max friction force and what's actually being applied.
Say that again?
You have like a maximum mu static and then what's
Right, so
actually
in
being
static equilibrium, the frictional force that is being experienced is 433, right? Because we did sum of the forces in the x. The x component of 500 is equal to this. We got 433. But in order for the frictional force, in order for movement to occur, it has to be 525. So is A and B moving? No. Did we have to go do that? We could look at it, but that's not really what we needed to do in the problem. The problem never asked us, is there impending motion between A and B? But if you're curious, and we went ahead and found it out. you have to find the frictional equation, you have to find the frictional force using static equilibrium first before you determine whether you could use this, unless you know impending motion is going to happen. Okay? So, we looked at what was given, what we had to find. We only had to find P, which means we only need one body and one equation. But then we looked at all the forces that are present in the problem, and there are 5 unknowns, which means we needed 5 equations and 2 bodies. So we knew somewhere in between was what we needed to do. You guys chose, why did you choose this free body diagram and not the other 2? Say it again? Least number of unknowns. Here, there are only 3 unknowns. If we separated these 2, we now introduce 2 more unknowns. So let's minimize the number of unknowns. So pick A and B together, and you were able to use 3 equations to solve for what P was. And P turned out to be 1583. So what does the question say? It says, is the system in equilibrium for P is equal to 2500? No, what's happening if P is 2500? It's moving to the right. Both blocks are moving to the right. And then B, what's the maximum force P for which the system is in equilibrium? What is the maximum force for it to be in equilibrium? 1583. You just used equilibrium equations to find that P is 1583. When P is greater than 1583, what's going to happen? It's going to move. If P is only 100, what's going to happen? If P is only 100, it's not moving. So this is the maximum value. This is the value at which movement starts. I think friction problems are the hardest. I think friction problems are the ones that could cause your mind to make it think it's harder than it is. I think that's how I would describe it. Because it's very methodical, it's the same way we've done all statics problems, right? You could just start to ask too many questions at times with these friction problems. The problem could look more complicated than it is. Yeah.
So we analyze it as if it was about to move. Did we actually pick a direction to say it's about to move this way?
Yes, because look at where P is.
Okay.
Right? If P is 0, the blocks are not going anywhere. But if you start pulling on P, which way is the block going to go?
Well, I'm thinking, yeah.
If you're going to start pulling, if P has a value, which way is it going to go?
Yeah,
It's going to the
it's
right.
going to the right.
And we had to decide on the direction, otherwise we wouldn't know which way the frictional force goes. Other questions? Joe? Yeah.
I'm still
Yeah.
confused about why we didn't write the frictional force AB.
For in between. Okay, so let's just, everybody's comfortable with the given, right? Everybody's comfortable with the find. Everybody's comfortable knowing if we only need a P, we only need one equation, right? Everybody's comfortable writing this. With this, you had 5 unknowns, so you knew you needed 5 equations. Everybody's good with this, right? Okay, so at this point, you have to figure out what free body diagram you want to draw. And we wanted practice, so we drew A only, we draw B only, and we drew A and B together. So you look at this problem and you say, okay, if block B is being pulled by P, we know there's eventually motion here. We don't know if there's motion there, right? But we know there's going to be impending motion here. So I know I can apply my frictional force here. When I separate A and B, I'm making this problem way more complicated. So I'm never going to go there. There's no way in hell I'm going to solve that. I'm only going to stick with these guys because I know there's motion here and I don't know what's happening there. But if you went ahead and you did separate them, and we did do the math, we would have found that they didn't move separate. But I think this is complicating things, you don't need to go here. You think about which free body diagram do I want to use first, and you choose this one, because there's only three unknowns here. Okay? And here, this one, you might say, oh, well, free body diagram A only had 2 unknowns, but they're not even asking us to find those unknowns, so why the hell should we even do it? Right? They want us to find P. Let's stick with the free body diagram that has P in it. And this one has P in it, but then there's 5 unknowns. I don't want to do this problem. Does that make sense? Okay? So you know you have to analyze one body. You know you need at least 1 equation. You might need upwards of 5. So, but the main thing is P. So you pick a free body diagram that has P in it. So that crosses out A. You don't even want to look at A. So you have a choice of either doing this free body diagram or this one. But this one has 3 unknowns in it. 1 that you know, and 1 that you have to find, and the other 2 that you're going to maybe have to find. Here, the one you have to find, and now we have 4. We don't want to do this. We want to stick with this. I'll only bring these into the picture if I have to go there. But I didn't need to, because 3 unknowns, 3 equations. That's better now? Paul, you had your hand up in the